paper chromatography, well, first, before we start and dive into this experiment, I want to give you a little bit of background on paper chromatography because I know we went over in class, but some stuff you may have just forgot because this is in the earlier part of the year. Alright, so paper chromatography is one method of testing for purity in substances and identifying compounds. It's really useful because unlike a lot of other methods, it requires a relatively small amount of materials. I mean, you need that little dot of whatever substance you're testing. It's relatively cheap and it is relatively quick. I mean, you're not spending 6 hours waiting for it. It goes in about an hour tops. So this is how it works. When color chemical sample is placed on the paper, and then the paper is placed in a little container of solvent, the solvent diffuses up the paper. And so, for my experiment, I'm using water as a solvent. So remember, like dissolves like. Since water is very polar, polar molecules are going to be dissolved by water. And so, the more polar the molecules, the farther up this molecule will travel, because the water's traveling up, and so it'll bring with it the most polar molecules. So when you have two different things in the same substance, they're gonna be different, so they're gonna have different chemical structures. So different chemical structures means you're gonna have different polarities. So you're gonna have it travel different distances, and that way you can distinguish, say, if you have put green in, and then blue and yellow, which are make up green, have different polarities. So you're gonna have yellow, and then you're gonna have blue up higher. So that's just an example. Also, if you're not using water as a solvent, which water is the most common, keep in mind if you're using a nonpolar substance that it will dissolve the nonpolar, so you'll get a very different result. Hi, my name is Ann Dieter, and today we're going to be looking at the dyes in Skittles using paper chromatography. This is a method used to purify and identify different substances, like the dyes in Skittles. Right now, I'm in my dad's lab, but you can do this experiment at home because it's super easy and super simple. So the first step of this experiment is to dissolve the dye off the Skittles. So what you're going to do is you're going to put them in a small disposable cup like so. And then what you're going to do, get the dye off, so you're going to take a small pipette of water, squirt it in there, and then you're going to swirl it around a little bit until it starts to turn green. So you can see this is starting to turn a little green in there. And so you're just going to wait, and you're going to do that with all different colors. Okay, so what I've done here is this is a piece of filter paper that I've cut into a rectangle, and I have labeled this is red, green, purple, orange. So now I'm going to put the dye that I got off the Skittles onto one of them. So what I'm going to do is put this on, and then I'm going to put it on red. So let me show you what that looks like. See that small red dot on the R? Now we're going to do it for all of them, and we're going to let it dry. Okay, so what I've done here is this is a piece of filter paper that I've cut into a rectangle, and I have labeled this is red, green, purple, orange. So now I'm going to put the dye that I got off the Skittles onto one of them. So what I'm going to do is put this on, and then I'm going to put it on red. So let me show you what that looks like. See that small red dot on the R? Now we're going to do it for all of them, and we're going to let it dry. Okay, so we've let this dry, and it's important to let it dry, otherwise when it's wet it'll just leak off in the water and you won't get the result you want. Alright, and so I also did another one. This is just pure food coloring. These are the actual colors that are in the Skittles. I use this kind of food coloring. And this is a control group to just see if we're getting the ideal results that we want. And so here I have a square rectangular container. There's a little bit of 1% salt solution that I made by mixing 3 cups of water with about a quarter teaspoon of salt. And so this is going to be our solvent, what we use. And so what I'm going to do is I'm going to pick up my piece of chromatography paper, and I'm going to put it in here. Okay, so we're done with the experiment now, and this is the food coloring thing. Remember how I did a control? Well, this is the control. This is the idealized version. These are the actual dyes in the Skittles. And so you'll see that this is red, this stripe right here. I put red food coloring here, yellow here, green here, and blue here. And so this is the result I got. So this is red here, this is yellow, pure yellow, and then here's green. So green is not green. Green is like yellow and blue. So this thing comes as so much a surprise. If you remember back to kindergarten when you were trying to make green and you only have primary colors, and it's like, oh, mix yellow and blue. So this is basically what they do to make the dye. They don't have a green dye, they create a green dye. And so by using paper chromatography, we were able to ascertain what is actually making up a substance. Alright, so now we have blue. And so blue is a real surprise because blue is a primary color. And then you have this red stripe in the blue. And so I was like, oh, what's going on? But apparently there's red and blue combined to make the blue color that you see on the Skittle, or in the food coloring. Alright, and so now we have the Skittles. This is the Skittle one. So this is orange, purple, green, and red. So those are Skittle colors. So this did not come through as vibrantly as the other ones, but that's because the dye we got off the Skittles wasn't as concentrated. Because you have to get it off the Skittle, it's in the water, it's not like pure food coloring which you'd use, and it's very bad to get on your clothes. So here you have orange, which is one pure color. Then you have purple here, which is pretty much purple. And then you have green, which is again a combination of yellow and blue. You see it's a little faint there, but it's there. And then you have red again, which is pure. Alright, so this was a really fun lab, but there's some finer points that you have to, they're careful points that you have to make sure you do. First of all, as you can see, you want to make sure you get the Skittle concentration as concentrated as possible. So what I did after a little bit is I use these things called micropets. Yeah, they're not small dogs. They're like little things that are like, they're little glass straws, like so, and you would put them in the little plastic container that had the Skittle and the water in, and you would put it in, and then you would drop it onto the sheet. And then another thing is that when you have everything all dropped out on your sheet and you have that glass thing, you want to be very careful not to like dunk it in, because that short circuits the whole thing. So you want the solvent to hit the tip so the solvent can rise up. If you get the solvent everywhere, it's just going to rise. It's not going to rise past your dye and bring it up. And that's pretty much my experiment. Thank you. So another important point in paper chromatography is the retention factor, or the RF factor. So basically, the retention factor is distance traveled by the substance ratio to distance traveled by the solvent. So in this little diagram, you can see the solvent went up to this arrow right here, and the substance went up to this arrow right here. And so you would put, say this is 2.1 centimeters, you put that up here, and then the solvent went, say, 2.8, you get an RF factor of 0.75. For example, in my paper chromatography, you can see that the blue or the green went up very high, but if I use, say, a different solvent, it might be different, because solvents, the RF factor depends on the solvent and the substance. So to get accurate picture, use the same solvent for all your substances to make identification. And an extra point is the RF factor is never going to be more than 1, because in no case will the substance travel farther than the solvent.